Okay guys, today we are doing 5.2, which is limits. You have to watch the other two YouTube videos before you can watch this one because it's going to make your life that much easier. They're both only like 3 or 4 minutes each, and this one isn't going to be very long either. So make sure you do that to put yourself in the best possible situation for being successful with limits. So we're going to start with the definition of a limit. The limit is the intended height of the function. So it's where the graph plans to go. It doesn't mean that it's necessarily where it actually goes. Okay, so here is our notation for the limit. The limit as x approaches some value, let's call it a, is equal to L. So we'll go through that as we go through this set of notes, but notice as x gets closer to a but not equal to a is what we're actually looking for. So I'm going to underline that too, because intended height and this are pretty much saying this the same things. Okay, so you're getting closer to the a, like infinitesimally closer to that, so as close as possible without actually having to equal the a value. Sometimes we can equal the a value, but not always. So what we're going to look at right now are these 3 different graphs right here that all represent the exact same limit. So this first one right here, we have a graph and it has a solid dot. And as we approach the a value, which we don't know what it is, but as we approach it, coming this way, it has a height of L, and coming in from the right, it also has a height of L. So we would write that the limit as x approaches a of the function equals L. Okay, that's fine. But then we get to the next problem, and in the next graph, we actually have a hole in the graph. And so the thing is that the limit is the intended height of the function. So even though there's a hole in this graph, it very well looks like this graph intended to go through that point, but for some reason it didn't. So this limit is actually L as well, because that's the height that it intended to reach. So here's our formal limit notation. And then here's that final graph right there, which also has a hole, but then up here there's f of a. So this graph was intending to go through a height of L. It actually jumped up to this height right here, but remember that the graph, or the graph of the limit, or let's just say the limit, is the intended height of the function, not the actual height. Okay, so this one, even though it has a dot up here, the limit is all the same. Now I'm just going to make a point up here. If I asked you what the function value at a was, because there's a closed dot, this would be L. It has a height of L. If I asked you what the function value would be at a, this would be undefined because there's nothing there. And then finally here, if I asked you when you plug in a what you would get, because the closed dot is right up there, that would be f of a. So you're being asked 2 separate questions. One is the intended height and one is the actual height. I'm going to call it the for real height, because whenever you have f, that means for real. So it doesn't really, but you guys know. We're just trying to look for things that help us remember. So f means for real, like where is that solid dot? You had to color it in. Where is that one? So here there isn't a solid dot, so that f of a is undefined. Here it's at the same height as the limit, so the limit and the for real value, f of a, are the same. And then here f of a is just f of a, and it's not related to the limit. Okay, you already watched the diner example, so this is the situation when the diner is no longer there. It caught fire or something, I think the video says. So in this first example, it says find each of the following using the graph. So we have our graph right here, and we want to know the limit as x approaches -2. So here's -2, That's where x equals -2. And as I come in, the limit is always intended height. Where does it look like the graph wants to go to a height of? It looks like the graph wants to go to a height of 5, right? What's the for real value, or f of -2? What's the actual value? That's this guy right here, because there's a solid dot, so that's 3. Okay, so this is going to take a little bit getting used to. First of all, it would make no sense for mathematicians to come up with a completely different notation, like the limit as x approaches -2, and then have it mean the exact same thing as this right here. That just doesn't make sense for them to do that, so keep that in mind. But then also, you already know how to do this one, right? So we're keeping in mind in the word limit, there's an I for intended height, okay? And then the F represents the for real height. Super good English going on here. So the next one is the limit as x approaches 4. So here is where x equals 4. And I am intending, when I get close to 4 from both sides, to get to a height of, what is that? 7. So my intended height is 7. But what is my for real height, or my actual height? It's 2. Okay? We're going to add in 2 problems just because I want to. These were very specific examples right here where we have some discontinuity in our graph. But if I asked you, what is the limit as x approaches 2 of f of x? And then if I just asked you, what is f of 2? I want you guys to see the difference. So here is x equals 2, right here. Positive 2 this time. And the limit is the intended height. So as I come in from the left and the right there is my intended height, and it's 6. But what's my actual height? Well, at 2, my for real height is actually also 6. So sometimes limits can equal their actual heights as well. Alright, so next we're moving on to a certain type of notation. They're called one-sided limits, which is super strange for some people because you've never seen this before. So right here, this says the limit as x approaches a negative. So notice that the negative is not in front of a, it's actually like in the exponent spot, and that just means that the limit as x approaches a from the left-hand side. And the reason why it's from the left-hand side is because it's, and they use negatives because generally speaking, our negatives are on the left. So I'm just going to write that in there to give you a friendly reminder. So as x gets closer to a from the left, but not equal to a, that's what we're saying is our intended limit there. So for example, when I'm doing x equals -2, I'm just looking at this piece because this is to the left of -2, and then anything on that side would be to the right. So what do you think we're going to use to notate right-hand limits? So to notate right-hand limits, we use the positive, and the reason why we do that is because positives are on the right of the number line. Okay? And same thing when you're coming in from the right. The left and the right hand limit on all 3 of these x values we've chosen are exactly the same, but they won't always be that way. So we'll take a look at that in a second. So the last thing before we look at more examples, and pretty much are almost done, is that you need to know that the limit of a function only exists if the left-hand limit and the right-hand limit are the same. So you might want to write that down because that's in symbolic notation and not in words. So we're just going to write for the limit to exist, for a limit to exist at L, the left-hand limit and right-hand limit must be the same. And then what's really cool if you've ever watched Mean Girls is if that left and right hand limit are not equal, then the limit does not exist. So, you know, that's how she wins like the mathletes or something. The limit does not exist. So we abbreviate that in math as DNE. It's different than undefined. So limits do not exist, and our for real values, our function values, are the ones that are undefined. All right? So if I'm moving too fast, you can pause. If I'm moving too slow, you can speed it up. That's a great thing about having a video on YouTube. All right, let's go up here. It says find the following limits. So this is going to be a left-hand limit as x approaches 1 from the left. Okay, so you go here. I always draw this, but it's not necessary. Some of you can do it without it. This is the left, this is the right. So as I get closer to 1 from the left, what is the intended height of the function? It's equal to 2. Now as I approach 1 from the right, that's this guy, as it's coming in, what's the intended height of the function? It's 4. So what is the limit at 1? So you go to 1 and you're like, wait a second, one of them's 2 and one of them's 4. Remember, those numbers have to match. So at an x value of 1, the limit does not exist. All right, let's take a look at an x value of -1. So that's happening right here. So as I come in from the left, that's this guy, my height, my intended height is 2. And as I come in from the right, which would be here, my x value is 2. And because the left hand limit and the right hand limit both match, my limit at -1 is also 2. So I'm just going to draw this in again. This is the left, this is the right. Okay? Moving on to the next one, we got a bunch of discontinuities in this here, which we will talk about later, but basically you're not able to draw these graphs without picking up your pencil, so they're discontinuous, and obviously there's a more formal math definition that we'll get to, but let's just get into this one. So we're looking at x equals 0, which is this line right here. So until you get really good at these, I would always encourage you to draw a left side and a right side. So at 0, we are coming in from the left. So when I come in from the left, that's this side, I'm going to come up and my intended height is 2. And when I come in from the right, my intended height is 1. So at 0, because there's a discontinuity, the limit does not exist. But what is the function value at 0? I absolutely need a closed dot at 0. So that's the for real value. So that equals 1, because that's where there's a closed dot. If both of those were open dots, then it would not have a function value at 0, so it would be undefined. All right, next one is where we're looking at -2. Oh my goodness, there's a lot going on at -2. Left, right, so when I come in from the left, I'm right there, and my intended height looks like it's 0. Yeah. And then when I come in from the right, that's this guy on the right side of that line, my intended height is, what is that, -2. So because those two numbers do not match, and because there's a discontinuity, the limit does not exist. I should say because there's a jump discontinuity. If there is a removable discontinuity, the limit would still exist, but we'll get into that in another lesson. Okay, but what is the function value at -2? So right here is where the closed dot is. So I'm just going to highlight these right here. So the function value equals -1 on that guy right there. Okay? All right, well, what if your graph looks like the next one? What if you have this right here? So you have a rational function graph. So you have x over x minus 1. So here it's asking you about 1, which they've drawn an asymptote there. So this is where x equals 1, and this is the left and the right. So let's see, they want to know what the function values or what the intended height is on the left-hand side. And that is something you haven't seen before, but that's going to be negative infinity because it's going to go down, 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 down. Okay? And then our right-handed limit, which is this guy right here on the right side of the line, I'm going up, 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 so my intended height is infinity. What is the limit as x approaches 1? Well, are these exactly the same? No. So the limit does not exist. We have an infinite discontinuity there. But what is your function value at 1? So where's your closed dot here? Well, usually graphs can't cross their asymptote. So in this particular situation, there is no value for f of 1. So it's undefined. Alrighty. Next thing we're going to go over is what do we do if we don't have a graph and we just have equations? We're going to keep this very simple. So if you just have equations, we're going to be working with 3 of them. The first thing you need to know, and you might just want to write this down, is the limit of a constant is the constant. So what that is saying, it doesn't matter what value of x you're approaching, it'll always be the same number. So for example, right here, I have this graph right here is y equals 3, or we could write f of x equals 3. So if I said, what's the limit as x approaches 2 of 3, which is what this graph equals, the answer would be, okay, well, when it approaches 2, which is right here, when I come in from the left it equals 2, when I come in from the right it equals 2, so that must mean, when I come in from the left it equals 3, and when I come in from the right it equals 3, so that must mean that the intended height is 3. Now because this graph only has a height of 3 and doesn't change its height at all, it doesn't matter if the number here changes, like let's say it was -5. If I'm here at -5 from the left and the right, it's still intending to reach a 3, so the answer is 3. So if you just have a constant number here, then the answer is the constant. So the limit of a constant is the constant. Okay, what if you just have the limit of x? If you have the limit of x, then you just get to, as x approaches a, your answer is always whatever that a value is. So for that one, let's say I have the limit as x approaches -2 of x. So if I go to -2, tie it back to that graph, when I come in from the left, it's -2. When I come in from the right, it's -2. So whenever you have an x, it's just like taking that -2 and plugging it in. Okay? Which is exactly what the next property says. It's called the DSP, or direct substitution property. As long as f is a polynomial, which we will only give you polynomials, as long as f is a polynomial, then anytime you want to find the limit of an equation, you can just plug that a into the equation. So I just want to point out this equation right here is not a polynomial. So you shouldn't just be plugging into things like that. But like I said, I won't be giving you ones like that either. So you just have to know for now, if we ask you a question to find the limit about an equation, then you just plug in whatever x is approaching, which is what we have on our very last example right here. So we're going to review those properties. So first of all, this is the limit as x approaches 0 of 6 is 6, right? So what this rule is saying is that you have your function always equals 6. So it's always like that. So it doesn't matter where you're coming from in the x direction, it's always going to have the same intended height. Now this one right here, the limit as x approaches -3. So -3, but 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is y equals 9. Is going to be 9 because the limit of a constant is the constant. Then we get to property C. This is called the identity property, but really because x is considered a polynomial, once you start putting variables in, all you do is plug in. So if I were to plug 5 in for x, the answer would just be 5. So maybe I'll do it like that so you can see that I'm plugging in. What about this? As x approaches -1. Again, I have a variable here, so I'm just going to plug -1 in for that variable, and that's going to be equal to my limit. So if you are like, I'm kind of hazy on that, you can either just memorize to plug in, or you can always graph y equals x, which is this guy right here. And if you graph it as x approaches -1, because it's x, you're just going to get that -1 as well. Okay? And then for our last one, x squared plus 3x, that is a polynomial. Polynomials are the addition or subtraction of monomials, and monomials are the product of variables with positive exponents and coefficients. That was a lot. I'm not expecting you to memorize it, but there are nice clean problems that we can factor or long divide. You've been working with them ever since you started algebra. So for this one, I want to know the limit as x approaches 1. So I'll do 1 squared plus 3 times 1, which is equal to 1 plus 3, which equals 4. All right. So real quickly, briefly, I'm going to show you the graph of this. So normally, nope, not normally. I have it right here. I'm going to show you this in a graphing calculator. Could totally graph this by hand, but for the sake of time, I'm not going to. So we have x squared plus 3x. Okay, and then I hit graph, and this is what the graph looks like. So the question is, as x approaches 1, well, here's 1, and here's the height of the function. So as x, there's no holes, no gaps, so when I look at this, when x is 1, the intended height is 4. So if you're not sure, or if you want to double check, and I'm allowing to use graphing calculators, like on a midterm or something like that, then make sure you utilize the resources that you have. Alrighty, that's it. Adios.